Sequences. Informally speaking, a sequence is an ordered list of elements. That's similar to a set, but unlike a set, order matters. Precisely, a sequence is a function whose domain is the ordered set of natural numbers, and natural numbers are the positive integers. Now we can list the elements of a sequence. We often do this with curly braces. Example, the first 4 odd numbers. We'll use our curly braces to enclose our sequence. If we wanted to write an infinite sequence of positive odd integers, well, we could do that as well. We want to clearly demonstrate a pattern before we use an ellipsis to show that this is an infinite sequence. Take a look at these numbers. 2, 3, 5, 7, 11, 13, 17, and then I'll indicate that they go on forever. This is actually the infinite sequence of prime numbers. How about this one? Now I've written down a few of the first terms of this sequence. Do you see the pattern? We love to search for patterns. Do you know what number comes next? Have you found the pattern yet? This is our Fibonacci sequence, recursively defined. Listing the elements of a sequence is informative, but we may also, so I had a bullet here, we can list the elements of a sequence. But we might also use an index, that is to use indexing, where the terms are denoted by a variable. So I've written a few out here. The a sub 1 is our first element. A sub 2 is our second element. Our nth element is written a sub n. The one right before the nth element is written a sub n minus 1, and the one following our nth element is our a sub n plus 1. Imagine the first terms of some given sequence. Here I've given you the first 5 terms. Now our job might be to determine the nth term. Our nth term will be here. A little notation, since a sub n will denote our entire sequence. This would look fine. I'm going to leave a little bit of room before I put my other curly brace on here. The nth term is going to exist here. Leave a little bit of room, and it's going to go on indefinitely. So there we go. Now imagine looking at those first 5 terms and wishing to write the nth term. We must understand the pattern. So I'll do a little bit of scribble work. This is my a sub 1. This is my a sub 2, my a sub 3, a sub 4, and a sub 5. Ultimately, I'd like to recognize the pattern, so I could write the nth term using the index n. Here I have an index of 1, index of 2, 3, 4, 5, etc. So as I look for that pattern, I try to recognize the numerator is increasing by 1 and starting at 2 when n is 1. So I think a clear choice there would be an n plus 1 for our numerator. Now I'm just going to quickly check to see if that holds up. For my index of 1, I get a 2. My index of 2, I get a 3. And my index of 3 is a 4. My index of 4, I get a 5. I think we've convinced ourselves that our numerator for our nth term looks good. The denominator that I see is 1, 3, 5, 7, 9. Looks like I have those odd numbers. So I know I need to be able to write this nth term as an odd number. I have to make sure that when n is equal to 1, I get a 1. So I think about that for a little bit. And I come up with a guess here of 2n minus 1, and I'm going to see if that holds up. When n is 1, I do get 1. When n is 3, when n is 2, I get a 3. When n is 3, I get a 5. When n is 4, I get a 7. When n is 5, okay, I think we've got it. So we were able to write the nth term. This is our nth term. I'm going to be very specific as I write out the nth term, just so I can focus on the notation. A sub n is our nth term. Which looks like this. And this is a proper way of writing the nth term. There we go. List the first 4 terms of the sequence. Given the nth term, it's parentheses negative 3/4 to the n. When n is 1, our first term is negative 3/4. How many do I need? I need 4 terms here. There we go. When n is 2, I have a positive 9/16. Looks like they're going to alternate in sign as I have that negative enclosed in the parentheses. So the next one up is negative 27/64 and 81 over 256. The next one, the 5th term, would be negative 243 over 1024. And well, we could list these all day long. Our calculators will produce the sequence too for us. You'll notice under list, list is right here above our stat button. And then moving over to options, we can call up our sequence, number 5, and state the expression for our sequence. I can declare any variable I want. I could use n like it was given to me here, in which case the variable is n. And I'm going to start with 1, and I'm going to end with 4. decimal approximations might not be all that convenient for us. So if we use the feature in our calculator under our math menu, convert it to fractions, it may be a little bit easier for us to quickly read and record. Try another example. We're given a sub k is equal to 5k plus 1 and b sub k is equal to the quantity k minus 1 cubed plus 4k plus 2 for all integers greater than or equal to 0. State the first 5 terms of each. In this case, we're starting with the subscript 0, as it indicated that, and let's find those first. Letting the index k equal 0, I get a 1, then a 6. Letting k equal 2, I have an 11. Letting k equal 3, I have a 16, and letting k equal 4, I have a 21. Looks good. Now I'll do something similar with b. Taking an index of 2, get the same 11, so it looks like they're shaping up to be the same. But we'll notice what happens here. They do not agree here by their fourth term, because remember we started with an index of 0. I think I've got a 45 here. I think what I'll do is I'll grab my calculator and I'll check this just to make sure we can use this efficiently also. So let's take a look here. Now, if you don't feel like typing in the k for the variable, you could use an x. In fact, I'll do that here just to demonstrate that you can pick any variable that you want. X minus 1 to the third power plus 4x plus 2. The variable that I was using was x. Now, should I wanted it to match the k, I certainly could have done that. Here we're starting with a 0, and we're ending with a 4. That'll give us the 5 terms. I'm not sure how I did it, but I accidentally typed in a negative. I don't know. Maybe as you were watching it, you saw that happen. I didn't see that happening. Oops. There we go. Back on track. So what if I wanted to add up a certain number of terms, starting with 0 through 4? If I wanted to add these all together, well, certainly I could just find each one and then add them all up. Let's take a look at what we should have here. Did you get 85? That'll be our sum. So we have some notation for this if we wish to add up, starting with k equals 0 and ending with 4. We could use this summation notation. Joseph Lagrange uses this capital sigma to represent this summation, where we have, and I'll look at this one here as our example. So here we have 1 plus 6 plus 11 plus 22 plus 45, like this. That's our B1 plus our B2 plus our B3. Oh wait, I'm sorry. We started with 0. That was a B1, B0, B1, B2, B3, there we go, B4, I've got them all, like so. Now your calculator can do that also. So let's take a look. I'm going to call up that last sequence. There we go, okay. Found the sequence in here. And I'll use that same list feature. Over underneath math, you'll notice number 5 is our sum. So we can ask for the sum of a sequence. It agrees, it was 85. Now we see another example for the summation of this 2k squared plus 7, starting at k equals 1, ending with 3. So we'll find this sum first of all by hand, and then we'll check with our calculator to make sure we have a good understanding. So when k is 1, our first term is 9, and this indicates that we're adding to it. When k equals 2, I have a 15, and when k equals 3, 25. Looks like we should have 49. Now we can do that by hand, probably quicker than we can with the calculator, but let's just give it a try here. I'm going to use k for the expression this time. Make sure I have the variable listed as k. We'll start with 1 and end with 3. This will give me the terms that I'll be adding together. So actually what this gives me is the sequence. What I'm going to do is I'm going to add them together. We'll just take the sum of our sequence to get our 49. Sigma represents the sum, and capital Pi is product. The index here is an I, and we're going to start with 3 and end with 7. We're going to multiply instead of adding. So I think I'm going to need a little more room for this example. And I'm going to show when I equals 3, I equals 4, 5, 6, and 7. So I'm going to do this one by hand. I just want to see what's happening here. There we go. What I'm doing is I'm just putting in my index into here. So I've got 3 times 5 divided by the product of 2 and 4. And then I'll continue to do that. Now what I need to do is I need to multiply all of these factors . I do see some convenience in here, which I'll take advantage of. And I do feel like checking my work here real quickly. I'm going to grab my calculator. In that same list where we'll generate a sequence, grab my calculator and I typed in, I guess I used an X instead of the I. Thought that would be more convenient, starting at 3 to 7. And I'm going to go ahead and generate that sequence. And this gets a little bit difficult to see, so I'm going to convert that to a fraction to see if I have those. There we go. Now I can quickly check to see if I have those right. Gives me the simplified version. There's also a feature in our calculator where we can, just like the sum of a sequence, we can take the product of a sequence, and that's what this notation is saying, the product of the sequence. So to call that up, second list, under our math menu, oh, look at that, there's a product feature right here. I'll take the product of that sequence. Oh, I must have hit something not wrong. Let me try that again. Oh, I had the fraction. Delete that out of there. There we go. I'll put the fraction at the end of it. 63/8. So it looks good. Lastly, we'll look at n factorial. N factorial is defined by your number n times its next one smaller, and continue that pattern all the way down to 3 times 2 times 1. I like to think of the analogy talking about how many different ways people can line up at the door. For instance, let me just use an example here of 5 people. 5 people could line up at the door in 5 times 4 times 3 times 2 times 1 different ways, or 120. 120 different ways 5 people could line up at the door, because the first place at the door is 5 different ways. Now that one person's there, there's 4, then 3, 2, 1. That's really easy to imagine. 0 factorial, then, you could think of how many different ways could 0 people line up at the door. 1. Take a look at an empty door, and that's how many ways people could line up there. 1. So in terms of simplifying an expression that deals with factorial, I'll choose another example here. Let's go with 5 factorial divided by 7 factorial. Just another example. And I'll take a look at 7 factorial. That would mean 7 times 6 times 5 times 4 times 3 times 2 times 1, which I'll just write 5 factorial. 5 factorial times 1 is 5 factorial, and I can see that my answer then could be found very quickly. Take advantage of all the helpful features in your WebAssign, looking at the practice another version of the problem, read about it, watch it, different videos that are available, and continue to work. Contact me if you have any questions or concerns.